Okay, I'm going to restart so our YouTube friends can hear. So last time we talked about overtones and spectralism in brief in my last lecture, but today I want to focus more on spectralism, what it is, and how we can use it to think more rigorously about our performance and about mixing and production and that sort of thing. So the main concept at play with spectralism is the Fourier transform. So again, the math behind Fourier transforms is fairly complex, and so I don't really want to talk about it. I don't think most musicians are going to care or understand what it means. Exceptions exist. But the Fourier transform is not that hard conceptually. So when we think about a signal, something like this wave represents the note. Some note. So in this axis, we have time. And in this axis, we have, amplitude, or, something like that, amplitude, whatever. It doesn't really matter. So this is, a wave, a sound wave, through time. However, we can transform this wave because, again, just like I talked about last time, most waves are not pretty sine waves. They're, very complex periodic functions. So I'm just going to erase all this junk, and I'm going to draw, some new function. So maybe our wave actually looks like this. Kind of spiky, So that's our wave through time. The Fourier transform, we're going to take this guy and put it in a new dimension. So now we're going to have a new graph. Again, over here we're going to have amplitude, or volume, or whatever have you. And now in this x-axis we're going to have frequency in hertz. So now our graph might look something like this. So what does this mean? So on this graph, we're going to have, a scale. So here's 0. Maybe this is 100 hertz. Maybe this is 200, 300. I don't know why my screen's handwriting is really bad today. 400, etc., etc. So all of this is in hertz on the x-axis. And the y-axis represents basically the volume that you hear each of those pitches at. You can think of them again as like overtones. And so this will be in decibels. So I'll write dB. So the y-axis will not have 0 here. So this should be 0, like hertz. But the y-axis will, since decibels are a logarithmic scale, it'll be something else. So maybe this is like -10 decibels, -20, -30. So typically with these transforms, we don't actually even consider this axis because nothing should go below. Because this is a logarithmic scale. So really this would be basically zero noise. Or in other words, -infinity decibels. And I'm going to show you examples of these graphs in real time. So this is what the Fourier transform does. And again, if you remember last time, do you guys remember last time when I showed you that Desmos thing? I'm going to pull that Desmos thing up real quick, actually. Can you guys see Google? Don't talk about a caterpillar. Can you guys see my Desmos that I am pulling up? Okay, cool. Gotta sign in. Oh no, guys, don't look at my username and password, please. Just kidding, you probably won't have to see my username and password. Do I have saved graphs? Oh, don't ignore that. That's for another math problem. I don't know if I saved it. but I'm just going to recreate it real quick so you guys can see. Let's say we had sine of x, and then y equals like sine, maybe like 2 sine of 2x, okay? And so now we wanted to do, those are like the two components of our function. And now we'd have, yeah, Desmos does have accounts. Desmos actually links to Google accounts so you can save your graphs. It's really cool. I just forgot to save the graph that I made last time, probably. Or I wasn't signed in or something. Okay, so B. I'm going to make this B and A. Now I got to add sliders. Alrighty, so this is a bit of a mess, but so here's our two components. We have basically here in red is the fundamental, and then in blue we'd have one of the overtones. So again, we can mess with the amplitudes. So maybe it looks something like this. So the green wave is their sum, which is the resultant wave that we see. So here's our wave. I'm gonna maybe make it a little bit. Yeah, I like this shape, I think. Oh yes, that's good. We're gonna go like that. So here's our wave. So this is basically the graph on the left, the time domain waveform. So now if we're going to take the Fourier transform of this graph, the resultant graph is going to look something like this. So let me clear the screen. I don't know how to make Desmos provide a Fourier transform, so I'm just going to kind of sketch what it might look like. So we would probably we'd have a big spike, and then we'd have another smaller spike. So this big spike would be at whatever the frequency of our red guy is. So let's use red pen. So red was the fundamental, I think. Let me check. Yeah, so red is the amplitude of the fundamental. So in this case, it was whatever A was. So A, or sorry, the height would be whatever A is, because the height is the amplitude, the volume. So the height would be A, and then this would be whatever the red frequency is. And then here we would have whatever the blue frequency was, which was double that of red, and the amplitude of that would be B, whatever that constant B was. Close. So does that make sense to everybody? So basically what we're doing is decomposing the wave. We have this as our sound. We're going to decompose it into the constituent parts and look at the amplitudes of each part. I'll make B smaller than A. So again, the green is what the actual wave is. The red and the blue are the components, the fundamental and its overtones. And so the Fourier transform is going to graph that and basically give us peaks wherever we have the overtones. So the height of it corresponds to how loud that overtone is, because again, the y-axis is volume and the x-axis is frequency. So let's look at a real example. So earlier I recorded myself singing oo and e, just to give some examples of what those might look like. So let's just hit, this is in Audacity, by the way. So here is, whatever the wave that I sang was. I wonder if we can actually zoom in and see what the wave looks like. Just curious. Oh, look, you can. So we're going to analyze this section. I kind of want to make it smaller. In future lectures, I'm actually going to talk about what happens with longer sampling and the uncertainty principle and all that sort of thing, because there's some really interesting math that goes behind that, but I don't want to talk about it today. So why don't we just say it's this long? And now I'm going to hit Analyze, and then you click Plot Spectrum. Not enough data? Are you kidding me? All right, we have to make it longer. So let's say here to here. Nope. Here to here. Is that enough? Analyze, plot spectrum. There it is. The uncertainty principle is a physical thing as well as a mathematical thing. It's very important in the Fourier transform because you cannot perfectly know. you can't perfectly know the exact Fourier transform based on the graph, basically. Unless you are literally looking at all of time. So anyways, I'm going to talk more about that in the future. But so here's the example of what a Fourier transform might look like. So again, so this is the actual waveform of what I sang. And here's what the transform looks like. So on the x-axis, we have all of our hertz, which, again, correspond to frequencies. And then we have decibels in the y-axis. So let's look at where some of these points are. So if you guys can see, there's a cursor and then peak right here below the graph. You see where it says that? So if I hover, it'll give me an approximate peak. So it says I have a peak at 128 hertz, which corresponds to C3 according to them. So now let's look for where the next peak is. The next peak is at B3. So I'm going to just assume that that's just off and it's a C3. Pretend that says C3, okay? So that would correspond to the first overtone, right? Because we have C3 and then this should be a C4 if you just kind of round up a little bit. To see this frequency table, I'll generate it again. You highlight whatever segment of sound you have. You click Analyze up top. Then you click Plot Spectrum. And it gives you this frequency analysis. I suggest setting the axis to log frequency rather than linear frequency because linear frequency is ugly. I also recommend setting the window to be the Hahn window. That's just the default. Some of the others are nice too. Rectangular window is actually not bad. I'm a big fan of rectangular window if you want things to be a little more simplified. But yeah, I'm just going to stick to the Hahn window for now. And there's a lot going into what each of those windows means. I don't want to talk about it. So yeah, so we have our fundamental here at C3. You notice the next peak is approximately at C4. Just pretend like it says C4. That could just be me being out of tune singing, most likely. And then the next peak is at G4, which is the third overtone. Then we have C5, E5, A sharp 5. Ooh, that's the seventh overtone. And then C6, that's D6. So you see that all these peaks are corresponding. Yeah, it's just janky rounding, basically. But all these are pretty closely aligning to the overtone series, like I discussed last time, which is what we'd expect. You'd expect sound to roughly decompose into the fundamental and then the overtone components. Now, what I want to draw your attention to, and this is kind of the main point of the lecture today, is the overall shape of this graph. So obviously we have the peaks, but notice that the peaks near the beginning are much higher than the peaks near the end. So keep this in mind. So this is me singing an ooh vowel, okay? So I'm going to hit close, and let me zoom out of all this nonsense. Oops, too far. So now let's go over here, and let's zoom into this little waveform. This is me singing an E vowel. And isn't that interesting? You can already see, looking at the waveform, that we have the fundamental. I don't know why it's not the loudest, honestly. If I had to guess, if you remember, it had a very big bulge around the fundamental. It was very wide. Then I think that has to do with me not singing perfectly in tune the entire time. Like if I go slightly flat or slightly sharp while I'm singing, the fundamental is going to be off, and they just kind of have to average that. So I think, imagine like taking the area under the curve. The fundamental would be the loudest if I was perfectly on pitch the entire time. It's just kind of getting smushed out because I, can't sing exactly. Yeah, there's no reason for that mathematically. But yeah, so look at this waveform for a little bit. So notice that you have the fundamental, you can see it pretty well, but the fundamental is wibbly. It's very wibbly on top of it. And if you remember last time we discussed, that corresponds to, a very high overtone being emphasized. So let's analyze it and see if this is true. Oh, I didn't actually select a region to plot. Okay. We'll plot this region. Plot spectrum. So let's look at this again. So this time, my fundamental is a D3 apparently. And we have D4, D sharp 4. Okay. Again, just rounding errors. A4, D sharp 5. Yeah, these are rounding errors. I'm sorry that these are rounding poorly. Pretend like these are all rounding nicely. But anyway, there are peaks at all the overtones. But notice that the shape is very different. Previously, all of the higher overtones were very low. You basically had like the first 5 overtones and then it dropped off. Now we have a bunch of these peaks at very high overtones, you know. And this corresponds to the fact that I'm singing an E vowel. So thinking about this sort of spectralist shape can help you in thinking about what vowels you want to sing and timbre for your instrument. So I'm going to back out of Audacity for a little bit. So in singing theory or whatever, we like to think about warm vowels, or dark vowels versus bright vowels. So on one end of the spectrum, we have oo, right? And then we have this sort of spectrum of vowels going all the way up to E. So, in there we have like A, like the A vowel, ah, O. I should probably space these out much better. O, ah, E. Anyways, and so these corresponds relatively to Fourier transforms that kind of look like this. So basically, the farther you go brighter, the more higher overtones you have, and the less lower overtones you have in terms of volume. And so this is similarly why some instruments can sound nasally, especially based on style. So if you have a jazz saxophonist, they're going to be playing with a brighter embouchure, which is emphasizing these higher overtones, which gives it that bite, that sort of nasal quality. Whereas a classical saxophonist is going to be playing more oo, more mellow. And the reason that the oo sounds more pleasant, per se, is because, again, we have these lower overtones. We're thinking like C, G, E. These are basically the first 5 overtones are literally just C, C, G, C, E, and then another G, right? So if we're just emphasizing those first 5 or 6 overtones, which is what I showed earlier, that's a very consonant, warm sound. Whereas over here, we might have, okay, whatever, C, C, G, C, but then it drops off for a while, and then we spike back up with a bunch of random notes. Maybe there's a D sharp in there, maybe there's an F sharp in there, because the higher you go on the overtone series, the more clumped together the notes are going to be. And so this makes the sound appear a lot brighter, a lot more nasal, maybe a little less pleasant, a little less warm. So this is a really, really, really important idea, especially for singers, because you have so much control over your mouth shape and your formats and how you control your overtones. But it can be applied to pretty much any instrument where you have control over the tone. A piano player is not going to need this, but if you're a violin player, what'd you say? So bright/dark kind of means the opposite of what it means tonally here. What do you mean by that? Yeah, I think I understand. Yeah, we're not talking about bright and dark in terms of like tonality, where Lydian is bright, but Phrygian is dark. I'm thinking this in more of a sound. So maybe this warm/cold should be better. There would be better suited words here. But a lot of people also talk about a bright or a dark tone. Yeah, so think about maybe warmer vowels rather than darker vowels per se. But that's kind of the word that people tend to use. Yeah. I try to say bright or dark to refer to tonality and like the music rather than The timbre, I usually try to say like warm versus cool for timbre, but less people say that. So yeah, but any wind player or bowed string player really needs to think about this. So let me go into Audacity real quick, and I'm gonna try to see if I can do overtone singing. Might be fun. How do I zoom out? So if you guys aren't familiar with overtone singing, it's where you try to emphasize one particular overtone. I'm not great at it, but I'm going to try to see if I can do it because it might look cool. So like, basically you're emphasizing one overtone. I don't know if it sounds good through the mic. It probably doesn't, but let's see. So I'm going to zoom into the end. I was trying to emphasize the 10th overtone near the end. So let's go into that bit. Let's take this little guy right here. Maybe we'll pick this little chunk. Let's see what happens. I have no idea if this is actually going to work. All right, so my fundamental, it says, was a D3. So I'm hoping for an F sharp to be emphasized. Dang, I did not get that. I got a D. This is so sad. Darn, I was really hoping for that F sharp. This is a big rip. Okay. Well, that sucked. Let's pick a different segment. Let's see what happens. Let's pick this section. Dang, it's still emphasizing the D7. I'm bad. Alright, guys. You heard it here. I suck at overtone singing. Yeah, I wonder if we can import sounds. I don't want to try that now because it's going to waste time. But in theory, what should be happening is like your Fourier transform has like, you know, all your normal spikes here, and then it's like, weep. I don't know. That's what's supposed to happen. I'm just not very practiced at it. So just pretend like it happened like that. So yeah, so now I want to talk a little bit about how this applies to music production and music mixing. I'm not a music producer at all. I'm not very good at mixing. So, you know, take everything I say here with a little bit less credibility. But if you guys are familiar with filters, you know, like, what are they called? Like high pass, low pass filters, that sort of thing. Basically, a filter is, it's filtering out certain parts of the sound. So, you know, let's say that this is whatever our Fourier transform is. So let's do, so let's say we had a high pass filter. So I might be confusing the two, but the high pass filter, I believe, is just going to chop off basically all of this junk. If we had a low pass filter, we would just be chopping off all of this junk. So basically, the software is converting your sound into a Fourier transform, and then it's going to do an inverse Fourier transform after it cuts off parts of the, basically parts of the overtone series or parts of the graph. And so these filters really help in giving you the sound you want, and cutting off noise. So, you know, if I'm playing a piece of music, most of my stuff is going to be in this sort of range, but maybe there's some extra noise that's happening out here in this sort of zone, and this isn't part of the music. Maybe it's just frequency or feedback, or, you know, some issue with your mic. So you might want to apply a filter here to cut off all that noise. Now, and again, notice if you just had your time, you know, your waveform like this, it would be really difficult to try to edit out noise from that. How are you supposed to tell what's noise and what's intended? However, converting to the Fourier transform really helps with cutting out noise. Okay, so I did confuse them. So the high-pass filter is where you chop off the low end, and a low-pass filter is where you chop off the high end. My bad. Yep. See what I mean? Don't take everything I say with too much credibility. I only know math. I don't do music production. Some other things that are interesting is, you hear about like bass boosting or treble boosting, and that's an important thing in mixing too, is do you want your song to have more bass or more treble? And again, this is really easy to do with the Fourier transform. If we have a Fourier transform that kind of looks like this, then all we have to do, to bass boost it is basically multiply it by something like this. So we're just going to multiply these two graphs or add them or whatever have you, and then our resultant might look, more like that, where it's bass boosted. Alternatively, we could do, maybe we want to minimize the bass and the treble and just focus on the middle. We can just weight it with that sort of hump, And so now our song is going to have a lot more of the middle tones rather than bass or treble notes. Or I shouldn't say notes, but sound, That's kind of the general idea there. So there's not really much more I can say in the way of mixing. If you are a music producer or somebody that does a lot of mixing, I would experiment with different filters to see how they affect, the Fourier graph, the spectralism graph, just so that you really understand what exactly all of your filters and effects are doing. I have no idea because I'm not a mixer. So, any questions on that mixing? Like I said, I might not be that helpful, but hopefully I can answer anything that's conceptual. Yeah. Oh, no. There's still a little bit more that I want to talk about. I just don't want to be stuck on mixing forever because I don't understand it. So the sample's frequency can be used to identify if it would be better as a bass. I don't understand your question. So what you're saying is, can you use the Fourier graph to determine whether your instrument is like a high quality instrument, expensive instrument, that sort of thing? Is that what you mean? Yes, actually. One of the most important things about instrument manufacturing is how in tune your overtones are. So let's say, I'm I don't know, like a trombone manufacturer or something, and I'm producing trombones and I play on my trombone. Ideally, what you want to have happen is you have a nice little spike right here at the fundamental, and then, some more spikes. But you want it to kind of taper off fairly quickly. Generally, with trombones, you want the sound to try to be as mellow as possible. Cheaper trombones are going to have more junk in this sort of range, this range right here, because they're cheaper. They're a lot, that like metallic sound that you get from cheaper instruments is oftentimes just higher frequencies because the metal is very poorly tempered and it's just doing random rattling. as well as the construction of like the bell, for example. The construction of the bell is going to determine in large part where the focus or like where the end of the pipe is. So a well-constructed bell should have a very clearly defined end point for the sound to stop at. This will keep all of these overtones in tune. In other words, they're equally distant apart on a logarithmic scale, or on a linear scale, I mean. However, if your bell is poorly constructed, it's just kind of willy-nilly whatever shape, that endpoint could vary for the overtones. And furthermore, if we just had a tube that just ended like this, there's a lot of variability in this region for where the sound could stop at. So yeah, there's a big part of instrument construction that goes into that. So that's kind of the brass end of things. Like a violin, for example, or other wooden instruments with strings, guitars, the body of the instrument needs to be tempered so that the wood properly resonates. So, for example, on a violin, if we were to take apart a violin, like take the lid off, so maybe this is what our violin looks like. I don't know what a violin looks like. This, this is the worst violin ever. But if we took off this top lid and we flipped it over, what you would see is this little beam right here. And so depending on the thickness of this beam could change a lot of the overtones. So if this beam is too thin, then the wood is going to be doing a lot more random rattling, which again gives more, it makes it too noisy. It sounds cheap. Typically you want this beam to be somewhat thick, and you also want it to be more elevated in the center. I'm talking about uncertainty next time. Get out of here. You want the center to be taller as well, so that the center is stable. So if you think about the violin, so maybe here's a side profile of what this violin little bar might look like. The violin's vibrations are going to be just like a string. Like the body of the violin vibrates just like a string would. What the placement of that middle bar does is keep it, I guess, in tune. So there's less randomness. So, obviously we have this as the fundamental, but here's the first overtone, right? We want this beam to help keep this overtone in tune so that you don't have, just kind of random wiggling going on. So there's a lot that goes into each instrument. I'm not a luthier. I don't construct instruments, so I can't tell you exactly everything that goes on with the construction of an instrument. But there are a lot of things that go into instrument manufacturing that are going to adjust the Fourier transform to give you the desired sound. Definitely. So Caterpus mentioned orchestration. So I can talk a little bit about orchestration. I hadn't really intended to. But thinking about what family of instruments you want to write for, the Fourier transform is not going to really tell you much more than your typical orchestration class would. But it certainly helps to think about. If you're going to be writing for strings or, woodwinds, those instruments are going to have a lot more in terms of the higher overtones, especially like a violin or something, or the upper range of those instruments. If you're playing a cello in the upper range, it's going to sound a lot brighter than a viola would in its lower range, even though it's the same note. So you want to think about that. I don't think there's much that looking at the Fourier transform is going to tell you other than, can you find analogs to the vowels in the orchestral parts? Yeah, so your U's are going to be, I'll just make a little spectrum again to E. So your U's and E's, there's a pretty wide range that you can play with any instrument. You can play your trombone very mellow, or you can play your trombone very bright, as in jazz. But typically your U's are going to be your brass instruments, with the exception of trumpet. Trumpet may be over here. And the tenor trombone is going to be a little bit higher than the other brass in terms of U. So trombone. Incidentally, that's why we have the bass trombone, is because the tenor trombone has a brighter sound, even though the bass and the trombone, or the bass trombone and the tenor trombone have the same range. The bass trombone is a little bit thicker and a little bit larger, like physically, which allows it to have a more full sound, especially in the lower range, where, the lowest range of the tenor trombone, you're just going to kind of get this like mush. It's going to be very mushy, and there's going to be a lot of noise in the upper end if you're playing on the tenor trombone, whereas the bass trombone will handle those notes a lot better, which visually looks something like this, right? So that's kind of the brass family. The string family, they're pretty much all the same. The general rule of thumb, I would say, is the violin and the cello are going to be a little bit brighter overall, but all of this has to do with how you're playing. The string family has a very wide range in terms of ooh-ee thought of what it can play. Was the Wagner tuba preferred for a warmer sound? I don't know what a Wagner tuba is, so I can't tell you. And then for your woodwind family, your woodwinds are generally pretty bright as well. So, maybe the clarinet, let's just say that the clarinet is like here. Your oboe is going to be one of the brightest instruments. Oboe, English horn. The bassoon also emphasizes a lot of those things. So basically your double reed instruments are generally very bright. Yes, then probably if the Wagner tuba was preferred for a low French horn sound, then yes, probably. But the tuba itself is already a very, very warm instrument, so I don't know how much improvement you could do there. Tubas and euphoniums are both conical instruments rather than cylindrical instruments, and conical instruments are generally speaking a lot warmer than their cylindrical counterparts. I mentioned that the trumpet and the trombone were the main exceptions to the brass being warm, and that's because both of those are cylindrical instruments. Whereas the euphonium, the tuba, a lot of horns, fartiness, that's just bad playing. Your instrument should not sound like a fart. I'm sorry. But yeah, if you're blatting, that basically correlates to noise. A lot of out of tune overtones, a lot of overtones that should not be emphasized. Not much more to say about that. Just don't play like that, please. But yeah, as far as woodwinds go, pretty much everything is very E or ooh. Ooh, what about sounds that are of indefinite pitch? Okay, we can try that. I'm going to clap and we're going to analyze it, and you get to see for yourself. Ready? Stop. Okay, let's zoom in. I want to go this way. How do I go left? No, stop. I want to go left. We want to go to this guy. Look at that wave. Look at that. That's so ugly. That barely even looks like a wave. It's aperiodic. So if we take this and we do an analysis on it, so this is the main clap that you heard. It's going to be, oh, not enough data? Are you kidding me? I hate when it does this. It's probably because it sounds random. Analyze. Look at that. It's just a wall. It's just a wall of sound. Like any peaks you have, there's a peak at D sharp 3, there's another peak at B4, D sharp 5, G sharp 5, D6. Like all these notes are just random. And that's basically what an undefined pitch sound is there's no real fundamental, there's no real overtones, so it's just randomness, basically. There still are peaks and valleys. The nature of the Fourier transform is that it's going to try to find peaks and valleys, even if it doesn't even they don't have any real meaning. But yeah, that's kind of what noise is. but you can still tune drums and stuff like that. A bass drum is going to have a more clearly defined fundamental, and then just get noisy after that. Yeah, so what you want to do, if you want to make a percussion instrument that is bad at implying a pitch, just try to make it as abnormal as possible. So if you have a timpani or a bass drum or something like that, that's just a nice normal circle, those are going to actually be pretty decent at implying a pitch, and that's why we tune our timpanis. Even though the timpani's overtones are wildly out of tune, the fundamental can still be tuned up pretty well. Whereas something a bit more random, such as the snare drum, I don't want to close Audacity yet. A snare drum is a normal drum, but it also has the snares under it, right? And these snares are going to mess up the normal vibrations of the circular membrane, which adds a lot more noise. And there's just more collisions, more randomness, etc., etc. Generally speaking, percussion instruments at large are bad for pitch. So the thing with drums is drums are actually not terrible at being tuned, especially circular drums. It's just that the overtones do not match the harmonic series. And I actually am probably going to do a lecture on drums and drum theory in the future and discuss how the shape of the drum and other aspects affect the overtones. Because I think it's really cool. It's a little math heavy, uses partial differential equations. But I do want to talk about it. As for cymbals, I don't know. I don't know anything about cymbals, but I would imagine that it's, if you look at a cymbal from the side, or I should say when the cymbal is being struck, the first thing to understand about cymbals is that they don't just vibrate like an umbrella. So if you think of an umbrella kind of going between these two positions where it goes up, down, that's not how a cymbal vibrates. That's how a drum vibrates, but that isn't how a cymbal vibrates. From what I understand, the cymbal is actually going to kind of do this sort of thing. So if this is a top-down view, basically it's going down on two sides, but going up on the other two, if that makes sense. And then those are alternating. So I imagine that the cymbal is actually pretty similar to the drum overall. But yeah. So the same thing is kind of true of the cymbal. The cymbal has a very clearly defined fundamental. If you're going to hit like a gong or hit your cymbals, you could find a fundamental pitch to associate with it. The issue is just the overtones are very out of tune. So it's hard for the human ear to be like, oh yeah, that's definitely supposed to be this note. Because, wait a second, all these overtones are giving me conflicting messages. Yeah, so percussion instruments are not great at doing notes. Even marimbas and stuff like that have to be very carefully constructed if you want it to sound like a note. Oh god, yeah, don't use a bow. Well, I mean, it actually does sound kind of cool if you use a bow on percussion instruments. I played one piece where we bowed the vibraphone. That was cool. But yeah, overtone hell. Oh yeah, definitely. But that's just because it's emphasizing the fundamental so strongly. A bowed vibraphone is basically entirely the fundamental. It's very close to a sine wave. Probably about as close to a sine wave as you could get in real, using a real instrument, honestly. Incidentally, if you want to think about it, sine waves would be the purest ooh vowel is a sine wave. That kind of makes sense. If you ever listen to a sine wave, it kind of sounds like an ooh. Well, thank you. I don't know anything about mixing and mastering, but I do know mathematical intuitions for music. But yeah, closer to the E side, you get things like the sawtooth, the triangle wave, if you've ever seen that. That has a really kind of ugly Fourier transform? Why don't we look it up? Fourier transform of sawtooth. Let's see what it looks like. Yes, leave site. Maybe we have a good picture. So this is a picture of basically what the components look like. So those are like all the approximations. This is what the Fourier transform in the bottom looks like for a sawtooth wave. Look at that. And that's why the sawtooth sounds kind of bad, you know, kind of noisy a little bit, is because basically every single overtone is equal, give or take. We can look up the Fourier transform of like a square wave too. Square wave is a little less noisy. I think it's more similar to a sine. This is what a transform of the square wave looks like, apparently. And I think that makes sense. Again, the square wave is a pretty warm vowel, if you want to think of it like a vowel. And similarly, we have this spike at the fundamental, and then it tapers off pretty quickly. And I would recommend that you guys listen to different synths that have simple wave functions, you know, relatively, and then look up Fourier transforms, and maybe that'll give you some good intuition for what the Fourier transforms sound like, how to predict the sound based on just looking at the Fourier transform. I think it's a lot easier to predict the sound based on the Fourier transform than just looking at the waveform itself, you know. So I really don't have much more to say other than that. I got pretty much everything I wanted to say out. Are there any other questions about anything I talked about today? I kind of wanted the lecture today to be a little bit more off the cuff. Oh, it's called the Fourier transform because of its inventor. I'll find a picture of him for you real quick. Joseph Fourier. He's a mathematician, a very important dude. The Fourier transform was not originally designed for music. It was actually designed to solve the heat equation and do stuff with heat and other partial differential equations, because the Fourier transform basically gives you a general formula for the heat equation. So normally the heat equation is only solvable, only has a good solution when the heat is distributed like a sine wave. So Joseph Fourier wanted to turn any function into a sine wave. So what he did is he constructed this idea called the Fourier series, where basically it's what we were doing earlier. So I wish I could go back to Desmos. Maybe I can go back to Desmos. But it was that idea that I showed earlier of, I can't, oh well, of decomposing sound into its overtone components. So, you know, maybe we have this frequency and this frequency are like the components of this total green frequency, which is kind of like wibbly, you know, something like that. So if we can decompose in general any function, you know, in green into constituent sine wave components, then we would have a general solution to the heat equation, since it's very easy to solve it when you have a pure sine wave distribution of heat. And so that's why he created the Fourier series and then the Fourier transform, which allows you to, instead of decomposing a wave into, you know, these discrete components of sine and sine, we can compose any wave into like this whole spectrum of components. So there are actually two different Fourier transforms. There's a discrete Fourier transform, which might look like this. It would literally just be spikes, you know, wherever you had an overtone. And so this would be the discrete Fourier transform. But more useful to us in real life is the continuous Fourier transform, which is what I showed you earlier, which might look like this. So you're trading off accuracy in terms of like what is actually at the peak. You're trading off accuracy for practicality, basically. The discrete Fourier transform is really only useful in math and not really useful in real life. But I'm probably, the next lecture that I'm going to do is going to go a little bit more in depth into the Fourier transform. I want to talk about some of this stuff, constructing Fourier series, and I want to talk about the uncertainty principle and how that applies here. Why are these peaks like rounded off? Why aren't they just literally just spikes? Why can't we have that in real life? So that's what I kind of want to talk about in the future. I think the uncertainty principle is really cool. There's some great intuition for it, as well as some other things with the Fourier transform. Incidentally, the Fourier transform can be used. Yeah, so here's the issue with the discrete Fourier transform, though, is not everything can be described uniquely using the discrete Fourier transform. So let's say, for example, and this also has to do with the uncertainty principle. So let's say I had, a nice signal that just, did this same pattern literally for all of infinity. If we knew that it did this for all of infinity, then we could take the discrete Fourier transform of this bit, and we would get something that looks like, spike, spike, spike. That'd be great. However, we don't know that it'll do that forever, and real sounds are not perfectly periodic. So to take the Fourier transform of a sound that is finite, maybe we just have a signal that just kind of looks like this. We don't know if it's going to loop at all, but we can still take the Fourier transform of it. We just have to add in that aspect of variance or uncertainty. The discrete Fourier transform only works if you have a periodic function that is regular for all of time. If you have a sound that is temporary, that does not literally play for all of infinity without varying, then you're going to have to use the continuous version. And for you statistics people in the room, that there actually is a really cool formula for the variance, which is basically how wide this sort of peak is. The variance of Fourier transform has legitimate applications, which is cool. Again, I'll talk about that next time. I want to talk about uncertainty principle and all that. Any other questions? All right. I assume nobody else in chat has questions. But thank you guys for coming out. Hopefully I can see most of you next week. It's going to be, again, kind of a continuation of this. And also, if you guys ever have topics that you want to present on, I would really like it if other people did lectures and stuff like that. So if you guys have any ideas or are inspired to present, doesn't have to be about math. You could present about music history, music theory, anything. So let me know. Probably, I assume most people don't want to do presenting, but hopefully some people will. So I'll see everybody next week, I guess, at the next lecture, hopefully. So let me stop recording.